So cones are what we get with the same setup as previously. So all squared terms are present, and one of them is an odd man out, which by multiplying by -1 we can assume is negative. So we have 2 positive and 1 negative. But now we're looking at the level set of the same function, but a specific level set, namely the one where it's fixed equal to 0. So this is the one where we have no constant term in the equation. So let's see. If we take a equals b equals c equals 1 again, then we're going to be looking at x squared plus y squared equals z squared. Or actually, I guess I can back up and do that in 2 steps. So it's where that's set equal to 0. So by bringing it over to the other side, it looks like this. And so if we take square roots of both sides, then we see that z is allowed to be the positive or negative square root of x squared plus y squared. And so that you can already see what the traces are going to look like for this one. They're going to be circles, right? Or more generally, I guess, ellipses. But if we look at z equals 0 and crunch our trace, then what do we get for this guy? Well, this is going to be x squared plus y squared equals 0, which means both terms have to be 0. So we just have a single point. Now, if we go up a notch, then we're going to be at z equals 1, and we have x squared plus y squared equals 1, and we have a unit circle. And then if we go down to -1, then we have exactly the same equation, and so we also have exactly the same figure. There we go, and so on and so forth. So now the thing is, if we go higher, so if we go up one more level to z equals 2, then now we have 2 squared over here. So the radius is going to be 2. So this circle is going to be, it's going to have a radius that's exactly double what we had before. And same as we go downstairs. Oops, I lost my bottom deal here. There we go. And now if I draw this correctly, we should actually get a straight line coming down, connecting those. Hold on. Connecting those dots. Almost. Wait. Well, I did pretty good over there, except for, those little suckers in the middle are not behaving. Oh! I grabbed more than I meant to grab there. Oh shoot! This is tricky. Okay. There we go. Oh god, look at that. Perfect. Beautiful. Okay. And so there we are. Okay, so we have cones. Cones come in pairs. And so if we do a slice for a fixed value of x, say, what kind of things are we going to get? Well, we might have 1 plus y squared equals z squared, for example, if I fix x equal to 1. That is a hyperbola, right? That's z squared minus y squared equals 1. So these slices that you get by cutting it to find some trace, those will give you hyperbolas. Except, so that makes it just like the one that we saw in the previous case, the hyperboloid of one sheet, except that there's this special one. If I take x equals 0, then it's going to go right through the origin, and that point is actually kind of unique, right? So we end up, that slice would look like just the intersection of those two diagonal lines instead of a hyperbola. So the cones are sort of a degenerate case of a hyperboloid. That's what they call it, degenerate case. Not a very friendly name, is it? Even worse, one part of the cone, so this one right here, the name for half a cone is a nappy. That's a nap. So that's the bottom nap of the, what? Got a nappy cone. Poor cones. They must have been teased all through grade school.